Welcome to Unit 2, Lesson 25, Solving Problems with Systems of Linear Inequalities into Variables. Our learning goal today is to use systems of inequalities to solve some problems. We have one learning target today. Learning target number 1 is for you to be able to say, I can explain how to tell if a point on the boundary of the graph of solutions to a system of inequalities is a solution or not. For glossary terms, our first term is solutions to a system of inequalities. All pairs of values that make the inequalities in a system true are solutions to the system. The solutions to a system of inequalities can be represented by the points in the region where the graphs of the two inequalities overlap. Our next glossary term is system of inequalities. Two or more inequalities that represent the constraints in the same situation form a system of inequalities. Now we can begin the practice problems for lesson 25. Our first practice problem says Jada has P pennies and N nickels that add up to more than 40 cents. She has fewer than 20 coins altogether. Write a system of inequalities that represents how many pennies and nickels that Jada could have. So first, when we look at this, we can see that P represents pennies and N represents nickels, and that there are fewer than 20 coins. So this inequality could be written as P, the number of pennies, plus N, the number of nickels, must be less than 20. It cannot equal 20 coins because it must be fewer, and it cannot be greater than 20 coins because it must be fewer. Next, we can look at the money side. On the money side of this, we need to add up to more than 40 cents. So when we write this one, we would say P, because P represents pennies, and pennies are worth 1 cent, plus 5N, because nickels are worth 5 cents, and N represents the number of nickels, and it says it must add up to more than 40 cents, so it has to be greater than. It cannot be less than 40. It cannot be exactly 40. It must be more than 40. So these would be the system of inequalities. Now, number 2. Is it possible that Jada has each of the following combinations of coins? If so, explain or show how you know. If not, state which constraint, the amount of money, or the number of coins it does not meet. So let's check A. In A, we have P, which we're going to replace with 15, plus N, which we're going to replace with 5, and that would need to be less than 20. Well, 15 plus 5 is 20, and 20 is not less than 20. So it does not meet the first constraint. Let's check the second constraint. We would have P, which is 15, plus 5 times N, which is 5, and that must be more than 40. Well, 5 times 5 is 25, and 15 plus 25 is 40. 40 is not greater than 40, so A cannot be a possible combination because it does not meet either constraint. Now we can check B. We have P, which is 16, plus N, which is 2, and that would need to be less than 20. 16 plus 2 is 18. 18 is less than 20, so it does solve the first constraint. Now let's take a look at the second constraint. We have P, which is 16, plus 5 times N, which is 2, and that must be more than 40. Well, 5 times 2 is 10, and when we add 16 plus 10, we get 26, and 26 is not greater than 40, so B cannot be an answer because it does not solve the second constraint. Finally, we check option C. In the first inequality, we would have P, which equals 10, plus N, which equals 8, and that would need to be less than 20. 10 plus 8 is 18, and 18 is less than 20, so this does satisfy the first constraint. Now we need to check the second. In the second constraint, we would have P, which is 10, plus 5 times N, which is 8, and that would need to be greater than 40. 5 times 8 is 40, and 10 plus 40 is 50, which is greater than 40, so it also solves the second constraint, and therefore C is a solution to this problem. If you have any questions about how to solve this practice problem, please use class time to ask for further clarification before we move forward. Our next practice problem: a triathlon athlete swims at an average rate 2.4 miles per hour and bikes at an average rate of 16.1 miles per hour. At the end of one training session, she has swum and biked more than 20 miles in total. The inequality 2.4s plus 16.1b is greater than 20, and this graph represent the relationship between the hours of swimming S, the hours of biking H, and the total distance the athlete could have traveled in miles. My said, I'm not sure the graph is right. For example, the point 10, 3 is in the shaded region, but it's not realistic for an athlete to swim for 10 hours and bike for 3 hours in a training session. I think triathlon athletes generally train for no more than 2 hours a day. Number 1. Write an inequality to represent Mai's last statement. So, looking at the problem, we know that S represents the hours of swimming and that H represents the hours of biking. So if we were to add these together, S plus H, Mai said no more than 2 hours a day. So it could be less than 2 hours a day, or it could be exactly 2 hours a day. It just can't be more than 2 hours a day. So S plus H is less than or equal to 2 would be Mai's inequality. Number 2 wants us to graph the solution set to our inequality. So, using this inequality, if I let S be 0, then H must be less than or equal to 2. So on my y-axis, I can put a point at 2. On the other hand, if I let H be 0, then S would be less than or equal to 2. So I can put a point at 2 on the hours of swimming. Because this is a less than or equal to, that or equal to tells us we have a straight line, a solid straight line. So we can insert that here. And because we know we want it to be less, that means we would shade in everything below this line. Number 3, determine a possible combination of swimming and biking times that meet both the distance and the time constraints in this situation. So what we're looking for is a point that is in the overlapping double shaded area or on the solid line that is using a boundary of it. So if we look at our graph, going to 1 and going up, we won't be able to hit any area. But if we cut it at 1/2 and go up to maybe 1.5, it looks like we could be at a point inside the double shaded area or maybe on the line that's creating the boundary. So let's try it in the actual inequality and see if it makes it true. So this would be 2.4 times S, which would be 1/2, plus 16.1b, which would be 1 and 1/2, and that should be greater than 20 if this is true. So 2.4 times 1/2 is 1.2. And 16.1 times 1.5 is 24. Use a calculator here. 16.1 times 1.5, and that's 24.15. When we add 1.2 plus 24.15, we get 25.35, and that is greater than 20. So it does make that one true. If we try the inequality we wrote in number 1, s plus h is less than or equal to 2, then we would have 0.5 plus 1.5, which is 2. 2 is equal to 2, so it does satisfy the second inequality as well. So a possible combination, which we have just verified, is 0.5, 1.5. It's in the double shaded region that makes the first one true, and it's on the solid line boundary, which makes the second one true. If you have any questions about how to solve this practice problem, please use class time to ask for further clarification before we move forward. Our last practice problem, Elena is considering buying bracelets and necklaces as gifts for her friends. Bracelets cost $3 and necklaces cost $5. She can spend no more than $30 on the gifts. Elena needs at least 7 gift items. This graph represents the inequality 3b plus 5n is less than or equal to 30, which describes the cost constraint in this situation. Let b represent the number of bracelets and n the number of necklaces. Number 1, write an inequality that represents the number of gift items that Elena needs. So as we look into the word problem, we can see Elena needs at least 7 gift items. We can also see that B represents the number of bracelets, N represents the number of necklaces. So for number 1, to write an inequality that represents the number of gift items that Elena needs, that means when we take the number of bracelets and we add it to the number of necklaces, at least 7 means it can be greater than 7, it can equal 7, it just can't be less than 7. So this would be our inequality for number 1. Number 2. On the same coordinate plane, graph the solution set to the inequality you wrote. So, what we can do is if we allowed b in number 1 to be 0, then that tells us n must be greater than or equal to 7. So we can go to 7 on the n-axis, and we can put our n-intercept. Now we can do the opposite. If we say that necklaces are 0, then that means bracelets must be greater than or equal to 7. So we go over to where bracelets are 7, and we put our b-intercept. And because this is greater than or equal to, That or equal to means we are counting the points on the line. So we're going to use a solid line. So now we have our solid line connecting them. Then we need to know which side of that solid line to shade. Well, since we want them to be greater than or equal to, we know that if we stuck 0, 0 in there, it wouldn't be true. So we don't want to shade down and to the left. We want to shade up and to the right. So we're going to shade everything above and to the right of that line that we just drew. So now what we're saying is everything in this yellow shaded area and the solid line that created it all makes this equation from number 1, b plus n is greater than or equal to 7. The yellow shaded area and the line creating the boundary make it equal. So now number 3. Use the graph to find at least 2 possible combinations of bracelets and necklaces that Elena could buy. So what we can do is look in the double shaded region, down here where the yellow shading and the blue shading overlap and create this green shading. So anything in that green shading and the solid lines that form the boundaries for that green shading. So what we can do is we could find this point right here, which is at 7, 1, and that would be one possible solution. Then we can look for another point in this green shading, and I see this point right here at 6, 2. These 2 points could be combinations of bracelets and necklaces that Elena could buy and meet both sets of constraints. It would give her enough gifts and it would keep her under budget. Number 4. Explain how the graphs show that the combination of 2 bracelets and 5 necklaces meet one constraint in the situation, but not the other. So let's see where this lands us. If we go over to 2 bracelets and up to 5 necklaces, we find ourselves right here. This point, 2, 5, meets the constraint for number of gifts, but it's above the constraints for budget. If you have any questions about how to solve any of these practice problems, please use class time now to ask for clarification before we take the end of Unit 2 test.